Okay. Okay.
All right, Ben. So take it away when you're ready.
Okay. So today's lecture will be on functional derivatives in physics. And I guess this lecture stemmed from me trying to do some functional calculus in a physics setting and not really knowing what I was doing and just kind of using the notions that had been developed in physics textbooks, but no one really defines what they're doing. So I was calculating things in a way that I didn't really understand what I was doing. So this kind of inspired me to really dive a bit deeper and to actually try and come up with some definitions. And this lecture is basically a summary of what I found. Yeah. So as some motivation for why functional derivatives are interesting, in physics, well, in theoretical physics, we think about fields a lot, and we think about Hamilton's principle a lot, where we're interested in looking at varying the action and then setting that equal to zero. Now, I'm just going to do the manipulations that we do in physics, and I'll define them later, but this should all be fairly what's the word? Fairly standard knowledge to a trained physicist. Sorry, to the mathematicians, but okay. So the variation of the action is just going to be, well, the variation of the Lagrangian, which is also a function of some fields. So we'll have fields, and we'll also have derivatives of fields. And it will be evaluated at some coordinate x. The Lagrangian is a functional of those functions, and likewise the action is as well. And we apply this kind of chain rule that we often see in physics, where once we vary this Lagrangian, we simply go ahead and write down what looks like chain rule. So we go Lagrangian, so a mu, variation a mu plus something like this, where we're treating the derivative of the fields as its own functional. And then we take the variation of that. So that looks like chain rule, but I haven't defined what that operation is. We'll do that later. In most physics textbooks, that's kind of just assumed it's some small thing that looks like a derivative, but okay, we'll be more precise here. Right, okay. So what do all those symbols mean? If you're looking at classical mechanics for a point particle, a variation, and if you're in particular looking at like a pendulum, say, a variation just kind of moves you through the configuration space, a small amount. But now we're doing functional calculus. So what does it mean to move through the functional configuration space? So I've gone from coordinates like x, y, and z, and I've promoted those to functions, and I'm treating them in the same way. I'm treating the functions as x, y, and z, and I'm going to vary these functions. Okay. Now, in point particle mechanics, we'll see things like normal derivatives of x, y, and z, these normal variables. And you can think of a derivative as basically the infinitesimal rate of change. So if we call something like this, say that would be delta f. And then over here, this would just be delta x. Then the derivative, so f dash of x, is just going to be the limit as delta x goes to 0 of delta f over delta x. And it's fairly intuitive and easy to understand what delta x going to 0 means. You're just moving closer and closer. But now we want to do functional calculus. So what does delta a mu going to 0 mean? What does it mean for a function to get small? I'm somehow changing a function. That's just a weird notion. Now we'll develop some formalism that is abstract and defined, but this is how we're thinking about these things. They're somehow getting small, and we'll see what we mean by they're getting small. Okay. Right. Okay, so the basic outline of this lecture will be to define all these symbols that I've spoken about, these variations and functional derivatives. And along the way, I'll be providing many examples to kind of illustrate what the definitions actually buy us, and they kind of mimic what we would expect in normal calculus. Yeah. And from there, I'll prove a chain rule for functional calculus. There are 3 chain rules that I'll state, and I'll only prove one for time reasons. And at the end of this, I'll derive Maxwell's equations using the formalism that I've developed here. Okay. Any questions before I move on? Oh. Okay, so definition of a functional goes as follows. So it's a very simple thing. A functional is just a map from the space of all, I'm going to say infinitely differentiable functions because it makes things easy, and to the n because I might consider many functions. So I'm going to take a map from this space to the real numbers, and then I'll say the space of all functionals will be denoted as this, I don't know, calligraphic F, well, not calligraphic. What do you call it? Math BB. Right. So this looks like in symbols. What I'm saying there is F, an element of the functional space, implies that F of, and square brackets will denote functional dependence. F1, I'll explain what I mean by that dot notation in a second. Fn is a real number for all these functions in C. N. Okay, so yeah, what I'm saying here is if I feed my functional f a bunch of functions, I will get a real number back. And what I'm doing in this dot notation here is just to kind of remind us that these are functions and they will need an input. It will be useful to keep track of what that input is later. So for now, it's left as empty. But essentially, you're feeding the whole function into the functional. And to see what I mean by that, let's look at an example. So we can consider a very simple one. So I'll define this functional as being an integral from a to b dx f of x. That's a valid functional. I get a real number at the end of the day. Okay, you have to assume that this is an integrable function, but okay, we're not going to talk too much about this sort of stuff. But this will give me a real number at the end of the day. And I've fed this whole function into my functional. We could also do something like f of dot is equal to dx, some weight, times f of x. Again, I get back a real number. And in fact, I could have, this one, we already encountered a functional earlier. If I give an explicit example, we could look at, let's say, the action for, let's say, scalar field theory. So you would have something like d4x, 1 over 2 dou mu 5x, dou mu 5x minus something like this. Oops. So that's another example of functional, and a common one that we might see in physics. Okay. Now I'll define a variation to mean, okay, well, yeah. So to define a variation of a functional, we need a functional f. And I'm going to define this piece of notation where I have circular round brackets to kind of indicate that I'm thinking of this whole thing as now just a function of alpha. So what I've done is I've taken my functional and I've shifted it by some alpha times a gamma at that particular function space. Right. And now I can think of this whole thing here as just a function of alpha, not a functional, but just a function of alpha. Okay, and then I'll define the variation to be this quantity minus the same quantity, but when alpha is equal to 0. So I see some confused faces.
Yeah, it's just so hard to think about the fact that all of these little f's, and in addition to the gamma, are at this point more or less completely arbitrary.
Yes. Well, okay, you have to assume things like integrability.
Yeah, but like, it's a pretty light set of conditions.
Yeah.
So it's just hard to think about, but I don't, everybody else is okay, I'm happy to be.
Yeah. Okay. Yeah, so yeah, what I was saying is that we need to think of this thing as just a normal function, not a functional, of the alpha parameter. And importantly, I'll assume that this thing is going to be differentiable with respect to the alpha parameter. And then we'll be able to do, let's say, normal calculus on this object.
Sorry, so it's a normal function, assuming that you fix all of your f's, right?
Yeah, precisely. So you fed it a bunch of f's. Yeah.
And
Yeah, exactly.
yes.
Yeah, exactly. So yeah, you feed the function, you feed the functional a bunch of functions, and you also feed it alpha times gamma, leave that fixed, but then you can vary alphas as you like. Right.
Sorry, also just are we leaving gamma as well unspecified? So we're not saying it's like a directional derivative in the direction of gamma, we're rather just considering it a function, a regular function of that alpha parameter.
Yeah, yeah, you're right. We're saying it's a directional derivative. So I could or should perhaps say that I should specify that I'm going in the gamma direction when I'm doing this specific variation. That would be more clear notation, but I'm just going to omit that gamma in what follows, and it will be implied. Okay, so a variation then, if I use the definition, was this thing here. And now what I can do is it's differentiable, and alpha is the real parameter, so I can basically just do a Taylor expansion of this. So the 0th order term will go away, but the 1st order term will stay. So I can go something like this. Do alpha, add alpha is equal to 0 times alpha, and then order alpha squared. And now I'm going to assume that my alpha parameter is small, so I can neglect these higher order terms. And I'm just differentiating this function with respect to that alpha parameter. The 0th order term that would be there got killed by this subtraction.
Is there no assumption of smoothness?
So I'm assuming that f is differentiable with respect to alpha, and that it's smooth enough that I can differentiate many times. Yeah. Also, so if I differentiated with respect to another parameter, I could also switch the order of the parameters. So it's smooth enough that I could do that. So what I mean by that is I could have shifted over here, let's say an fj, right? And I would have gone plus beta gamma j, and then differentiated with respect to beta. I don't know if that's okay. It's a little bit sidetracky, but it's smooth, so you can do things like this. Okay, so that's yes.
I guess the claim is going to be that that object, which is written as partial capital F partial alpha, the value of alpha is 0, that's going to be independent of the choices of the little s and the gamma.
Well, it's definitely going to be dependent on the gamma, so I should.
Okay.
I should specify the gamma in this notation, but I'm leaving it
Yeah,
as implied.
the notation is more or less standard, but that's good to know that
Yeah.
there's an implicit dependence on the gamma.
For sure. The way to think about the dependence on the F's is it's kind of like an order of operations. I pick a set of n functions here, and then I feed it to my functional, and then I do a variation. But I could have started with a different set of functions. So in some way, it's not dependent on that.
But in the physics context, those little f's are going to be the classical path.
Exactly. Yeah.
Okay.
Sure. Okay.
Sorry, can I just
Yeah.
correct? So this, the way you define it, where you sum over I.
Yes.
I mean, just sort of, if I think to like multivariable calculus and you have a directional derivative, usually I would imagine you sort of have your f of x vector plus delta x vector minus f of x over some sort of size. And so your derivative can be different depending where you're coming from. Here it seems like it's somehow you're just going in one direction at a time and then summing them all up.
You could have, yes. It's just a definition. I could have done something. So if I had considered, let's look at this quantity here. I could have also gone for something like this. So I could have gone fj plus beta gamma j. And then the sum, I could have done it for all n of those functions. And then if I differentiated, or I define something like this, I wouldn't have the sign. But when I do this derivative, you would get the same thing. I don't know if that's super clear.
Not really clear why you get the same thing.
Yeah. Well, for there, I see you're saying the derivative with respect to beta would be 0.
Yeah, exactly.
But I was imagining more like if you went from f of f vector plus alpha gamma vector, that wouldn't be the same.
Oh yeah, you'd have to go alpha vector times gamma vector, or like dot product, because you'd need a new alpha for each gamma, for each f basically.
Well, I don't know if you would. Well, to get the same answer, right?
To get the same answer, yeah. Do you want to? What was your question?
No, I just that fine.
Okay. Okay. Okay, so now we can talk about a functional derivative. Okay, so a functional derivative we'll define as a functional derivative of the functional f with respect to some function at a point x on your manifold will be denoted as this. So I'm not defining it, I'm just writing it down as this piece of notation. And it will be defined as this integral, or defined through this integral, I think is a better way to say it. So d is the dimension of my manifold, and I'm going to integrate this thing, which is just a piece of notation at this point of time, times gamma I, where gamma is arbitrary. And then this is going to be defined as dou alpha. I'm using some shorthand notation. Is everyone comfortable with what I mean by that? This, okay. Yeah, so then this is just going to be F1, Fi plus alpha gamma I. I need some more space. I lost them. That, okay. And then this will be Fn. So this is the first order term that we saw in the variation earlier. And this piece of notation is defined as, well, through this integral to be equal to that. Okay, and now I can, like I say, the gamma is arbitrary, so I'll pick a very specific gamma to kind of illustrate something, let's say. So I can pick this gamma to be the delta function centered at some coordinate y. And if I do that, I plug this into my formula. So I'll take this. This becomes a delta. So notice the notation, it's going to be minus y like that. And then this will be a delta to the d. And then this will be x minus y. And this thing is just going to be equal to the functional derivative evaluated at y. So we see that this piece of notation is equal to this object here, where I have specifically chosen my gamma as the delta. Right, so that's what a functional derivative will mean in this context. See some suspicious faces.
I think from upstairs, the partial alpha of capital F with alpha taken to 0, that's also what you call the variation of capital F, right?
Almost. If I had an alpha here as well, then it would be. So the variation of f was order, it's this derivative times alpha, whereas the functional derivative, there's no alpha. So I've just stripped off that order alpha term. Yes, so this I is not summed. So I'm looking at a particular, I'm differentiating with respect to this function. I could put a sum here if I wanted to, and then sum over all those derivatives, but I'm just looking at one of them at this point. So yeah, this I is not summed.
That expression defines df I.
This expression is definition, yeah. And then this is a result of that definition. Okay, so that will be useful. So we can look at some examples of how to compute these functional derivatives. So if I look at this functional, which as you can see is a functional, I will assume, yeah.
It's not a real number. Why is it?
It doesn't return a real number.
Yeah, you did.
Sorry, okay. I should have said that. It's if I leave that off, I mean from minus infinity to infinity. But yeah, you're right. Okay, so I use my definition, or I'm not using the definition now, but I know that this quantity is going to be equal to the alpha of f plus alpha delta minus y. And then I simply plug this into there, and I find something of the form, oops, f of x plus alpha delta d x minus y squared. Okay, and now I can pull this derivative into the integrals because this alpha is independent of x, and I can just do ordinary calculus with respect to the alpha parameter. So what I get is something of the form like this. Oh, that shouldn't be to the d, sorry. Two of those from, what is that called? Power rule law, times the derivative of the inside of that at alpha is equal to 0. Making a botch of this. Okay, and then this must be evaluated this bracketed term must be evaluated at alpha is equal to 0, which kills off this delta. And I'm left with 2 times f of x. And if I look at this derivative acting on this term, this f of x is independent of alpha, so that goes away. And this is just order alpha, so I get delta x minus y. And that will evaluate to 2 times f of y, which kind of resembles what you would expect in ordinary calculus if you're differentiating with respect to some differentiating a power. Yeah. Okay, so to do more examples, but for the sake of time, we can move on unless anyone wants more examples.
I just wanted to ask, following from this procedure, would you get that the functional derivative of a functional gives you back just a regular function? Like, or are we considering that last line to still be a functional of f? Because it no longer returns a real number if that's the case, since we've killed the integral.
Okay, so you're saying if I take a functional derivative of a functional, will I get back a functional?
Yes.
No, you get back a function. So
Okay.
Well, and in fact, actually further to Nia's point. So am I considering f of y a function, or am I thinking that y is a specific value that comes at the start, and f of y is actually just a real number?
it's so I'm fixing y, but in some sense it's a variable. So I'm taking this derivative at a fixed y, and I get out this result, but I can ultimately allow y to vary at the end of the day. So I just change this y at the beginning of my calculation. So at the end, I just get a function of y.
So then maybe to push a little bit harder, so you did a very nice job of clearly defining for the functional what the domain and the range was. The domain of functionals being this array of functions that are C infinity continuous, and the range was just a real number. And here it seems like the functional derivative, the domain is the domain of functionals, and the range is functions.
Yeah. Yeah. So this operation is a map from what notation did I use? F to C infinity.
I think why this is weird. This is got your specified point, and this is working for a specified point in your function. So if you have different functions in your functionals which are acting on different domains within your, let's say you have 2 functions in your functional, acting on completely different domains. And you now perform the derivative with respect to one of those functions, you have to choose a domain of that one function. So it's not arbitrary.
I only have one domain for all my functionals. So that domain is the manifold M, which I've specified. So this manifold will be equal for all of the functions.
Okay, so then why was it necessary to put a dot for all your functions? Like they could just be any, they could just all be. So all of the dots are representing some element of Minkowski,
for an instance. The dot notation is really just to tell us that when I have this delta, so I'm shifting by some, I'm imagining the function and then I shift by some parameter of that function. That's all that the dot notation is really used for. But you're right, that dot is signaling an input from some manifold Minkowski space, for instance.
Was it necessary to define a function to output a real number? Why could you say it outputted a function? Because at the end of the day, you're a derivative of functions outputting function.
Yeah, it wasn't necessary to do that, but that's the definition of what a functional is in like most places that I've seen it. Yeah, in fact, that when we think of a functional, it's a map from functions to real numbers. I'll define something a bit more general in the next piece of work. Okay, I don't know if that answered your question. Okay.
Would it almost be better to define this functional? So you said in your notation, partial capital F, partial lower f of y. Maybe to say, could you have defined, or would be better notational to define as partial capital F by partial little f of like circle? And then what you getting out of this would be, for your example, 2f of circle rather than y.
Yes, you could do that. What I would do is I would use a different circle.
Yeah, that's what I mean. Use dot here.
Yes, so here you could go circle,
Yeah.
and then you would have circle there,
Right.
but different from that dot. You could do that. It's sure.
Okay.
I don't know if that makes it better.
And then you have an integral t circle.
Yeah. No, you'd still have integral dx. So here I'm taking an element from the manifold, and I'm like explicitly doing it. Here it's abstract and saying that it depends on that element. I'm not picking out a point.
Okay, I see.
Yeah.
So that integral is taking everything from the manifold, and the circle is only telling you about a particular point of view.
The circle is telling me I need to put something in here.
Yeah, because then you have an awkward notation of direct delta x minus circle.
Yeah.
Collapsing to goes to the circle.
But I shouldn't think about y as a specific value, it's just a function. the
Yeah.
delta function.
Okay, now we can talk about chain rule, which is, I think some of the results here are new to what I've seen, which is quite cool, I think. But okay, before we get there, in ordinary calculus, if we have some functions that are smooth, we can compose f with g and then take derivatives of f of g of x, and you just get this chain rule where you think of just dividing fractions, but it's not really doing that, but it kind of looks like that. Okay, so you need to compose things to get a chain rule. Now, I'll ask the audience, does it make sense to compose two functionals? If I take one functional f1 and f2, can I put f2 into f1? No, because a functional returns a real number. I can't put a real number into a functional. Exactly. So what I need, or let me, for completeness, what I need is something a bit more general. I need what I call a function valued functional. So what a function valued functional does is it's a mapping from the space of functions, n of them perhaps, and it returns a function. And then the space of all function valued functionals will be denoted as that. I don't know if that's the best notation. If you have any better ideas, I would be very happy to hear them. Okay, so in symbols, what I'm saying is if g is a function valued functional, oh, that was terrible. Then that implies that g takes a bunch of functions, fn, and it returns, a function. And this is true for all functions f1. I need the notation there. To fn elements. Okay, so it's just one step of abstraction further.
What's the function value functional different to just a function? So when I can compose functions, gives me that function. Or if there anything happens in f of x squared plus g of x squared, another function.
I mean, Yeah. Technically, you can't compose functions like that, right? Because a function is a mapping from real numbers to real numbers. So you can't. Oh, right, because they have the same domain range.
Which inputs into the same as outputs.
Yes.
So in this case of normal functions, your domain and range being the same type.
Yeah.
That's basically function in function out. In order to compose.
Yeah.
The function inputs a real and outputs a real. And here we can put a function and the outputs of function. But yeah, I hear your point.
Kind of weird.
Totally, I'm sure there's some points. I'm going to write down functional building that, well, maybe it's an example, but imagine you could still say like function value functional is like f of x plus g of x.
Mm.
Yeah, it's not evidence. So, well, I guess it's f of dot.
That's
So it was f of dot, right?
sure.
Yeah. Yeah, f of dot, exactly. I'm not even. So I think in the other context, I'm going f of g. All right, I'm going g of f of x. So I'm like specifying x at that point. That I can do that. But in that,
you need to say h of x is defined as g of f of x.
yes, g of f of x. So I'm like,
that's a placeholder.
it's different to this placeholder, the dot that I'm using though.
But how can is that, I think, because you define your initial functional to output area on them.
Yeah.
If you just have your initial functional to be outputting functions, just when you know it does, like for it all be function value functionals, then would that not eliminate this confusion?
Yes.
Wouldn't that just give you back normal calculus? Or normal multivariable calculus?
No. So like this,
I mean, yeah, I guess.
this notation here is, you're not really differentiating with respect to the function. How do you even think of this? I mean,
Differentiating slots there.
yeah, exactly. It's not.
I could definitely believe as well that find something like a functional derivative, even if the function. What do you call this? Even if the functions and function returning functionals are the same, they could still be a different derivative, which is with respect to the functions that needs to be true.
I'm not sure I follow your question. So you.
I'm saying it's definitely different to do a derivative with respect to x, so derivative with respect to
F. Yes.
That's
Yeah.
I don't know.
Okay. Okay. So right. What did I want to do here? Okay. So okay. Now that I have these function valued functionals, I can compose function valued functionals within functionals or function valued functionals. So if I take a whole bunch of GIs, which are function valued functionals, then this quantity here is just a function by definition, and I can do something like G, where G is now a function valued functional of, I'm going to modify my notation a bit, but I think it should be clear. F1, Fn, another circle, which I'll explain. Okay, and then this will be a function valued functional. Okay, so what am I doing with the notation here? I'm imagining there's a GI here, there's a GI here, there's GI here, and so on. And each GI is dependent on these functions. So I run out of space if I want to write all of that. So that's why I have this set notation. Hopefully that's clear. But yeah, this is the idea of me putting or composing function valued functionals with other function valued functionals. Okay, so we can look at an example. So let G of f of this be equal to ln of f. So this is a function valued functional, and I'm leaving that input as open, let's say. And then I'm going to consider some G1, which is also a function valued functional. And this will just be equal to f squared. And then I can compose the two. So I go G of G1 of f dot, oh, and I'll evaluate this at some x. Then this will just be equal to G of f open circle squared at x. And this will then just be ln of f of x. There should be another bracket squared. And then, yeah, you can simplify that to 2 times ln of f of x. So that's an easy example of composition. And we'll use that example again when we do chain rule.
Evaluate it at x or at a function. It's G. Evaluate it at Z.
So yeah, so I need to evaluate it at some function. So I feed it a function f, and that's what I get back. I could have fed it a g or another function. So I could put in like an e to the dot there, if that makes sense.
Why is there an x? Like on the outside, so I thought these functionals supposed to take functions as an end.
So g is a function valued functional. So g returns a function.
It should also take a function.
It takes a function. So it takes in a function and returns a function. And then I could have left the circle there, but I'd need a third circle. Yeah. So here I'm just evaluating it at some. Okay. So now we can get to some of the chain rules that are interesting, I think, and useful for some of the other work that I've been doing. But okay, so I'm going to consider some function valued functional G, and then a set of function valued functional Gi, and then I'll compose them as follows, or as we saw earlier, and I'll just call that composition G of x. So there should be an x there as well, like that. Okay. And what you'll find is the chain rule looks like this. So if I go dou G of x with respect to j at some y, I'll get sum over a bunch of i's, an integral dz dou G of x dou Gi of z, dou Gi of z dou fj of y. Okay, perhaps it's worth defining what this object is. What I mean when I say that, that thing looks like this. So dou alpha, that alpha is equal to 0 of this composition. And then I shift one of them. So I shift the jth element, the jth function, by a delta. So I can just form this quantity by definition, and then what you'll find is that that's equal to this thing here, where this thing also has a definition. This thing is equal to something slightly different. So what I'm imagining here is I have G1, and G1 is a function valued functional, but I'm just going to omit its functional dependence for now. And then I'll shift Gi plus alpha delta D. What notation? I need, okay, let's do it like this. So these need circles. 0 minus y, and then Gn of 0. So the difference between this quantity and this quantity is here I'm shifting the functions, and here I'm shifting the function valued functionals. So I'm like outside of the function valued functionals. Whereas here I'm inside the function valued functionals when I shift. And I get something that looks like that. Okay. I can also get a chain rule for the variation, and that looks quite similar. You get something of this form, delta Gi of z. And I think, and then this one's quite interesting, is if you take a derivative with respect to x of g of x, you get the same first quantity, except now don't you z g of z. Okay, and then I'll prove this one, and the proofs of the rest are fairly similar. Okay, any question? It's quite warm today. Yeah. Okay. Oh, I should also mention that this one is only true if your original G function value functional doesn't have explicit X dependence. So as an example of something that does have explicit X dependence, I could have chosen to do, if I had something like that, this formula wouldn't be true because it has explicit X dependence. But if I have something like this, where f to the n whatever, that would be fine because there's no explicit X dependence. It's all contained within the functionals. If you have explicit dependence, this formula changes by a term, but we won't be worrying about that for now. Should be fine. Okay. So proof of the first one. So we're interested in proving this formula, and I have this definition. Maybe before I start this proof, how are we doing for time? Not great.
Yeah, what we do, we're doing 1 hour. I've blocked off 2 hours, but
I have as much time as people are willing to give me. So
you want to cut off an hour and reconvene, you want to go for 2 hours and reconvene.
we could
I think go for 2 and
Yeah.
2 hours.
Yeah.
Okay,
I'm sorry.
I'm gonna sneak out at 2 if that's okay.
that's fine.
If you see that at 2, would you want to it be included? I mean, he's getting to the punchline now.
Well, that's okay. I
All
don't
right.
see it, but
So maybe if we would formalize it to mono, it's the category here is to be. Wouldn't say it long.
Right. Okay. So what I'm going to do here is I have this definition, and I'll modify my notation just a little bit just to keep things shorter. So what I'm doing here, so I'm going to call this whole quantity G I of alpha j. and then that's going to be evaluated at some O. And then again, I can think of, oops, this gi alpha j as just a function of alpha, just a normal function of alpha. Okay. Okay, so what I'm going to do now is I'm going to do a Taylor expansion within the set, basically. So I can go gi at alpha is equal to 0 for some j. And then I'm going to take the first order derivative, the alpha, this whole thing times alpha. And then there'll be order alpha squared terms that we can neglect because alpha is sufficiently small. Okay, I'll change my notation, or no, I won't change my notation. So now I'm shifting all the GIs and I'm differentiating with respect to this alpha parameter on the outside. So this is the same thing as now just summing over all the GIs. So I'm going to go like this. Oops. I'll have G0, what was it? G1, 0, all the way to G, yeah, I need the whole thing. So it's going to be this whole thing, and then Gn. Okay. Of X.
The alpha j notation with, like, so it's alpha j with the f, means that you're taking the j's f and shifting it by alpha. Correct?
Yes.
And it's alpha times gamma, and gamma gets delta.
Mhm.
But now when you're using that notation for the functional, you need to be shifting a specific function, right? But that's not specified there because it's a functional. So are you shifting every function within that functional?
No,
Or is
I'm
it
just the jth one.
the jth function in the ith function? Okay.
Yeah. So gi of alpha is equal to 0 is just gi, basically, because that goes away and you just left with the gi. But yeah, exactly as you said.
Okay, so this is not a shift of functionals, it is a shift of the underlying function.
Within the functional, yes. Yeah. Okay, now if we recall the definition of a functional derivative, which I'll grab over here. So where we let's put that in gray. So if you look at what's going on over here is I'm summing over this derivative, which is that derivative. And then I have all of these. I'm basically just shifting. Oh, okay, maybe let me do one more line of manipulation, which I said, but I didn't write, that this thing is just that. When alpha is equal to 0, it's just the functional, the function value functional. Okay, and then we look at the definition. So this is that derivative. This is this function. And then here I'm going alpha times gamma, and gamma appears there. And in this case, what I would have is the derivative d to the d. What did I use? X. Yeah, let's use g. So dou g of x, dou g I evaluated at z, times the gamma. This gamma is this whole thing. So it's going to be dou alpha at alpha is equal to 0 of gi alpha j, and then evaluated at z. And now I'm going to expand this thing.
Is that integral with respect to, oh, there we go.
Sorry, yeah. Let's expand what that was. That was just gi of f, f j plus alpha delta d minus z f n, and then that's all evaluated at z. And then we can look at this, and this is just the derivative. I mean, this is just the functional derivative with respect to the jth term, where I have this delta, so this integral would collapse. And I just get this dou gi dou f j of oh no, this should have been y, sorry. Yeah, and that's the proof of the first one. The proofs of the rest are similar. I won't do them here though.
So where did the delta come from? Did we that from the gammas? Is that
This delta, where did it come from? So what I did originally was I defined this object and I shifted this by that. So that's where it's coming from.
just seems like is that a specific choice, or is it, I mean, it's we originally thought we were going to be independent of, or is this, I mean, is in that first step, what was the motivation for it, not delta, I guess?
So I wanted to, I guess the motivation is if we look at this definition of the functional derivative, I know in the case where gamma is a delta, that this is just this thing. So that motivates me to define this thing, and then I find out what it actually looks like.
I also just, it's some Googling, it seems like this, what the terminology other people use for this is an operator. Maybe this is something like this, an operator, it's like a derivative or something, right? Because it takes the version of functions to functions.
You mean the function valued functional is an operator?
So that's what it seems to say.
I saw that as well. I think I could have chosen operator, but I want it to be similar somehow to a functional. So it's like I don't want to be too far away from a functional. I'm really thinking of it as just a functional, as a one step of abstraction away from functional, whereas an operator kind of feels like an unrelated object. But sure, it's just naming.
It's the same thing.
Yeah, I
I mean,
suppose.
you could think about one G's as being the box operator, right?
Exactly.
So somehow spit out some other.
Yeah, you could do that. I think what I'm gearing towards in ultimately proving the transposition rule is I'm going to have things like the dependent field being dependent on independent fields. And that really doesn't look like an operator, but it could be an operator. So I guess I'm going in a direction ultimately it feels awkward to name it an operator. But you could. Okay. So we can do an example of this formula. So we can, earlier I computed this this composition. So I had this function valued functional and this function valued functional, and we found that when we compose the two, we get something like this. So I can take a functional derivative of this whole thing. So I can go g of x with respect to f at y, and by definition, this is dou alpha times alpha is equal to 0 of G2 of F plus alpha delta one dimension, so minus y, and I'll evaluate that at x. And you can just basically track where the function landed up, which is there. So I'll end up having something like 2 times ln of f of x plus alpha delta x minus y. Okay, and then I can use normal calculus here to find this answer, which will just be 2 over the derivative of this thing, which is 1 over f of the argument, and then I'm evaluating it at alpha is equal to 0. So this just becomes this times the derivative of the inside of this, which is just delta x minus y. So that's computing the functional derivative directly. I could also compute the functional derivative using the formula that we just derived. So I could go dou g of x, dou f of y is going to be equal to the integral dz g of x dg1 of z g1 of z dou f of y. And then we just have to compute this functional derivative and this functional derivative. Oops. So the first one, this guy looks like dou alpha of g of g1 of f dot open circle plus alpha delta minus z. So there I'm shifting like outside of the g, whereas here I was shifting inside the g, which is the difference. Okay, and then that's all evaluated at x, and then times, we'll need another variable, so dou beta of this quantity here, which is by definition just going to be plus alpha delta minus y at c. Yes, sorry. And then I can, here I'm, okay, let's just plug in what everything is. So here we'll have dou alpha g, what was g1? G1 returned f squared. So we have f dot squared and open circle plus alpha delta of x times dou beta. And this is going to be f squared. So it's going to be f of z plus beta delta c minus y squared. Okay. And all of that we will give us, oh, I should do one more step. G was the logarithm. Was it 2 times? No, it's just the logarithm. So then this will all be the logarithm. So here I'll have ln of f squared of x plus alpha. Yeah. x minus z. Cool. Okay, then it's just ordinary calculus. So the first one will be like 1 over f squared of x. And then I need to differentiate the inside of this. So this just becomes delta of x minus z. And then the second term is going to be 2 times f of z delta z minus y. Yep. Okay, now I can do the z integral, which will cause, I could do either or. I think I chose, yeah, let's do that delta. So everywhere I see a z, it becomes a y. So this becomes delta. Do I want to do it that way? Everywhere I see is, oh no, let's do this one. We'll make things easier. If I collapse this one, everywhere I see a z, it becomes an x. So then this becomes 2 times f of x, that, and then that's just 2 over f of x
The delta.
times delta of x minus y. Oops. Thank you. And that's what we found as well above. Okay.
Sorry, I put something I found wrong at the meeting that I did at 2.
Mm-hmm.
I'm gonna skedaddle.
Okay.
Might be best to.
There's only, like, all I have to do is do an application to physics next, which I suppose is the most interesting one. But we could stop here.
Maybe we just, whatever you. Let's do it with me.
Yeah.
Okay,
Yeah,
sounds good.
and I think it probably would be useful to let this sink in and read that.
Yeah,
Okay, that was really nice. Thank you.
Yeah.
For sure.
that's nice.
And borrow your evening. Young, able body. I am now completely envious of.
Neo, in case you didn't hear, we're going to stop here and we'll reconvene at a later stage.
Okay, sure. Sorry, what people are saying in the room is sometimes a bit difficult to hear from me.
For sure.
Okay,
Sure.
but thanks.
Thanks for coming.
Awesome. I really enjoyed it. Cheers.
Bye.